Hi, I'm Zhou, and I'm happy to be presenting a paper, Malicious Secure Multi-Party PSI with lower bandwidth and faster computation. This is a joint work with my wonderful co-authors, Kang, Yu, and Lijing. So this talk is going to be about private set intersection, so let's introduce what that is first. Private set intersection, or PSI for short, is a protocol between two parties, Alice and Bob, and they each have a set of input elements. The goal for the parties is to know which atoms are in the intersection. So in this case, there are R, I, T, E, and S. And as a result of the protocol, all parties know is the intersection of the sets, and nothing beyond. So ants won't know about any of Bob's atoms that are outside of the intersection, and Bob won't know about any of I's atoms that are outside of the intersection. PSI has several next applications. For example, if X signs up for a new encrypted messaging service, she probably wants to know which of her friends already use the service. The information that she wants is the intersection of her phone's contact list and the service provider list of clients. She can use PSI to compute the intersection without sending her contact list to the service provider. As another example, now there are lots of password managed applications, and they provide a service where any user can learn which of their passwords have appeared in a branch. This is an instruction computation that can be performed with PSI so that no one needs to send all their passwords to the application. As one more example, the advertisement provider uses PSI to measure the effectiveness of its advertising campaigns. They have a list of people who saw a certain ad, and the company who placed the ad has a list of who purchased the item. They can use PSI to understand how many people are in both lists. In the last couple of years, the most common approach to build a privacy intersection protocol was based on oblivious dual random functions. Oblivious dual random function, or OPR for short, is the distributed equivalent of a PRF in a synchronous setting. X only knows the output of the OPR on certain input values that she chooses at the beginning. On the other hand, Bob here has the key to the PRF and is going to get that as a result of the OPF protocol. He can compute the PRF value on any input he chooses of none.
Using OPF to build a PSI protocol, the approach is actually quite simple. I simply inputs all her elements into the OPF protocol and in turn gets the corresponding PRF values. Bob gets the OPF key and now can locally compute the PRF values for all of his inputs. And now he's just going to send those over in a shuffled order to Alice, who can then compare each of them with the OPF values she got for herself. And as soon as she has a match, she knows that the corresponding input was in the intersection. Multi-party PSI is the case where more than two parties wish to compute the intersection of their previous datasets. Similar to PSI, as a result of the protocol, all parties know is the intersection of the sets of all of them and nothing beyond, including the intersection of the sets of the partial parties. So far, MPSI protocols have been designed to support numerous applications. Multi-party access control is a scenario where several co-owners of a common content each specify a set of users who are permitted to access data. So the users in the intersection are allowed to access the content. Another application is helping several companies to plan cross-promotions. There, each company has a customer list, and they can use the MPSI protocol to compute the intersection of the customer list for which they plan special promotions where each list except the intersection is protected. One more example, consider a set of governmental or commercial entities wishing to collaborate to detect a possible intrusion attack to a common network. Each entity must protect the privacy of its information and its customers. And PSI protocols can solve the problem that finding the intersection of the set of suspicious IP addresses held by each agency without leaking any parts of the set except the intersection. The state-of-the-art MPSI protocol is built based on oblivious key value store and OPRF. Oblivious key value store, or OKVS for short, is a data structure with two functions, encode and decode. Given a set of n key-value pairs, we can encode them into an object S, and later we can use this data structure S to retrieve our key-value pairs. If we probe S on keys outside the set, we learn some value that we don't care about. When the associated values are random, it's indistinguishable that if the value got by probing the object S on an encoded key or some other key outside the set. It makes the key value store oblivious. Linear occurrence is a kind of occurrence that we can represent the encoding and decoding in terms of a matrix multiplication. For a linear occurrence, we can construct encode function as generating a solution to the linear system of equations. Each row is associated with one key. Decode function is a multiplication of key times s, and the result is a set of values that we are looking for. In this formation, the occurrence will have some kind of additively homomorphic property. Let's look at how the state-of-the-art MPSI protocol was built. The protocol is in the star topology communication model. P0, P1 until Pn are the n+1 parties who will compute the intersection of input sets x0, x1 until xn, where P0 obtains the output. For any x, each party Pi can compute a zero-share SHIX such that the sum of SHIX equals 0. P0 runs many instances of the malicious Q-oblivious PIF functionality, once with every other party, and then Pi obtains the key denoted by Ki, and P0 gets the set of the output of PIF of each set. To ensure that P0 doesn't know any of the intermediate intersection values from the two-party OPF outputs, unless all parties hold the corresponding atom. Parties use these zero shares to mask their OPF outputs. Each party Pi generates an OK with Qi, where decode Qh is the OPF output on H masked by the zero-share SHI for every H in X. Only if all parties hold an atom do the shares cancel out, revealing the presence of all OPF outputs. P0 constructs its OKVS Q0, encoding the outputs of all PIF of each set. The protocol results are the atoms in P0 set whose sum of the value in OKVS of all other party Pi is equal to the value in OKVS of each cell. Specifically, the OPF in this protocol is built based on vector oblivious linear evaluation. Vector oblivious linear evaluation, or VOLE for short, is a correlation generator that can be run between two parties. The VOLE generator outputs three vectors, U, V, and W, and scalar delta. So here X gets two vectors U and W, and Bob gets V and delta. All of these are still random, but with the property that they are correlated, and the correlation is such that W equals U delta plus V. If we can find a P such that MXP equals the transpose of HX, where M is a tremendous matrix as large as the full OPF domain, then we can construct two functions fx and fy, and their equivalent. Observe that the formation of MXP is the same as the linear occurrence. so we can use linear OKBS to construct it. Now let's introduce our results. We propose a new multi-party PSI protocol in the dishonest-majority malicious setting, which improves the above and PSI protocol in two aspects. First, we reduce the computation cost of LPN encoding for the central party P0 implemented in the PSI protocol by a factor of n, and reduce the total computation cost by 2 NL hash operations. Second, building on the above technique to improve computation, we use a tree architecture to reduce the communication bandwidth of the central party by a factor of n. To achieve it, we construct the PSI protocol by directly using VOLE in the multi-party setting. We make an important observation that a single random vector U is sufficient to mask the OKBS, so it is unnecessary to compute n random vectors. Thus, P0 is to generate n VOLE correlations with the same vector U by running a protocol with n different parties. We model this as a multi-party VOLE functionality MVOLE. Since we use the same vector U with each other party, the vector D will be the same, so P0 doesn't have to send it to each other party directly by itself. We use a tree architecture to transmit it, and we will introduce it later. We construct the PSI protocol by directly using functionality and VOLE as the underlying primitive instead of the OPF primitive. We adopt functionality and VOLE and an OKBS to obtain an OPF and simplify the computation of the output of OPF by removing redundant hash operations. Next, let me show you our tree architecture. We amortize the communication among all parties in a binary tree architecture. In this case, the central party P0 is to broadcast the message M to all other parties. The broadcaster protocol runs in top-bottom order. In round 1, P0 sends the message M to P1 and P2. In round 2, P1 sends the message to P3 and P4. P2 sends the message to P5 and P6, and so on. Then in this case, the central party P0 is to aggregate all the messages of other parties. The aggregate protocol runs in bottom-top order. In round 1, each leaf node sends its message to its parent. All the nodes that receive the message update the message and send it to the parent in next round. Finally, all the messages will be aggregated to P0. In conclusion, our results are using a single random vector instead of n random vectors in VOLE protocol and simplifying the computation of outputs of OPF to improve the computation efficiency, and using a binary tree architecture to reduce the communication bandwidth. Thanks for your attention.